Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. And this is just a summary of all the limit proofs that you should have gone through in your differential calculus course, and kind of drawing a common thread through all of them. So hopefully at this point, you have already been introduced to all the limit proofs, whether it's a finite limit at a finite point, also known as an epsilon-delta proof, or you have a finite limit at infinity or an infinite limit at a finite point, any of those. They all kind of have the same basic structure. So let's talk about that basic structure. The form they all have is the following. For any, and then we have a constraint on the y value. And actually, you know what, as we go through this, I'm going to use just a traditional epsilon delta definition to follow along. So for a finite limit at a finite point, which I'll note as FF, finite-finite. So x is approaching something finite, y is approaching something finite. Well, since y is approaching something finite, the constraint on y is you have an epsilon neighborhood about that limit, which is y equals L. Then we have this there exists statement. There exists some constraint on x. Well, again, with the finite-finite case, since x is approaching something finite, our constraint is a delta neighborhood. And that delta neighborhood exists as a bound around our central x value, which is a. Well, okay, so for all epsilon greater than 0, there exists a delta greater than 0 such that. And the next statement here is an if statement concerning x and the constraint on x. In other words, concerning, in this case right here, x and delta. And if it's a delta neighborhood, well, x is getting really close to a. It's within a delta neighborhood of a. So I'll write that in. There you have it. If the distance between x and a is positive but less than delta, then. And then the then statement is a statement about the function and the constraint that you have way up here on y. So let's see. In the finite-finite case, or the epsilon-delta case, the statement about the function is the function's getting really close to the limit L. And the constraint is we have an epsilon neighborhood. So that means that we're dealing with the distance between f and L being less than some epsilon. And that is the structure of the finite-finite case. All of the proofs follow this structure. So if you think about, for example, the finite-infinite case, that would be, again, that x is approaching something finite, but the function is approaching something infinite. Still, the structure matches this right here. You just have to use a little thought. You don't want to just copy everything. You don't want to have a list of a dozen different possibilities. Instead, you just want this, and you just have to think about it logically. Here, our function is approaching something finite, or I'm sorry, infinite. And so an epsilon neighborhood is out of the question. Instead, you're going to just have, in this case, a very, very large value, a massive value for an output. And that I just use capital M. You could use any letter you want. I use capital M. And so because our function values are running off to infinity, you are going to be challenged with a y value that's super massive. On the other hand, the x value is approaching something finite, so a delta neighborhood is in play here. And now I'll just go ahead and copy the structure from here. So for all statement about the constraint on y, well, the constraint on y is m is greater than 0. So for all m much greater than 0, Let's see. There exists a constraint on x. Well, there exists a delta neighborhood. Oops, and I should probably use the color that I've been trying to adhere to. So there exists a delta greater than 0, such that if, let's see, now we need the if statement here is a statement about x and the constraint on x. Remember, the constraint is delta. So, and our statement about x is that x is getting really close to a, and the distance between x and a has to be less than delta. So I'll just say that if the distance between x and a is less than delta, well then, and the last piece in green up here, statement about the function and the constraint on y. Our constraint on y is that we're dealing with a very positive, large positive value of m, and we want our function to be above that. So therefore, we want our function to be above that value of m. You could trade out, by the way, I'll call this the finite-infinite positive case. Infinite positive. There is, if you're into memorizing, like seriously, like a dozen different theorems, good for you. I'm not. But you could trade this out for the finite infinite negative case. In that case, again, you would have this limit as x approaches a. I have to zoom in so my pen does not get all jagged. So as x approaches a, of f of x goes to negative infinity. Again, since f is not approaching something finite, you cannot use an epsilon neighborhood. Instead, you have a very, very, very large value of y that you're dealing with, but it's very largely negative. On the other hand, x is still approaching something finite, so you do have a delta. So let's go ahead and start with our constraint on y. For all, let's see, our y value, oh, it's just an m. Very negative. So for all very negative y values that are handed to us, there must exist a constraint on x. And the constraint on x here is going to be the delta neighborhood, such that now we talk about the statement about x and the constraint on x. Well, x is approaching a, so it's within a delta neighborhood of a. So I'll just write if x is within a delta neighborhood of a, then, and now the last statement is always a statement about our given function and the constraint. The constraint on y is that we have this m, and we want our function to be below that because it's going to negative infinity. So then we want our function to be below that value of m. Again, it would be terrible if you memorized all these. The only one I actually keep in my brain is the finite limit at a finite point. The rest of them I create as needed. There are a lot of them. So I'm not going to list all of them here. I'm going to do one more. Let's say that you have an infinite limit at infinity. So let's say we have something approaching positive infinity for the x values, and the y values are going to negative infinity. So it's the infinite, but it's infinite positive, infinite negative. By the way, I just made up this notation. So it's not that this is an accepted notation throughout mathematics. It's just my little way of dealing with all the different languages it could be. So here is the case that I'm talking about. X is approaching positive infinity, but our function simultaneously is going to negative infinity. Okay, so this tells us we don't have an epsilon neighborhood because, well, our function is not going to something finite. So we just have a massive y value, but it's massively negative. And x is not approaching something finite either, so we do not have a delta neighborhood. Instead, x is associated with a very massive number that's positive, because it's going to positive infinity. Now I'm going to state my first statement. Somebody's going to walk in the room and they're going to hand me a constraint on y, specifically some value of m that's very, very negative, because the function's going to negative infinity. And I will have to find a very, very positive number n. So that's my constraint on x. That's a very positive number. such that if it's the case, I suppose that if it's a continuation of a sentence, I don't need to capitalize the I. If it's the case that now we need to say some inequality involving x and that blue n there. So x has to be greater than that blue n because x is going off to infinity. So I'm finding an appropriate entry point called n, such that from that point forward, all the x values I grab, their function values, end up satisfying this limit. So as long as I grab an x value greater than that n, then now I need a statement about the function and its constraint. Well, remember the function's going to negative infinity, so I need to get below this level of m I'm being challenged with. So I'm going to go ahead and say, then my function must be below that challenged level of m. They're all the same thing over and over again. I suppose the only one that I haven't given an example of is going to be the infinite-finite case. So let me give one of those as a final example here, and then we'll stop the video. So we have an infinite-finite case. Let me grab that. Infinite-finite, and let's go ahead and let the infinite be positive. No, let's go to negative infinity. So what is that case? Well, that's the limit as x goes to negative infinity of our function becoming some finite number L. All right, so again, I just kind of form the structure here. Notice I'm pre-filling a lot of stuff. That's the structure of all these. If you look at all the black ink, that's literally all the black ink in all of these statements. Let's see. Now I'm going to go ahead. I'll use green for the y values again. The function's approaching something finite, so an epsilon neighborhood is definitely in order here. The x value is not approaching something finite, so a delta neighborhood is not in order. I will need instead a very large number, specifically a largely negative number. All right, so let's go ahead and start copying. The function we have for all epsilon, this is our constraint on the y values, for all epsilon greater than 0. There exists, well, the constraint on the x values is that we have an n that's much less than 0, such that if now we need a statement involving our x values and that n, well, x is going to negative infinity, so it better be less than that n. So if x is less than that n, then now our statement about our constraint on the y values, which is epsilon, and our function, well, that would be that the distance between our function and our limit is less than epsilon. Again, all of these follow the same format. If I counted them up, you would have finite-finite, that's 1. You'd have the finite positive infinite, that's 2. You'd have finite negative infinite, that's 3. You'd have infinite positive, that's 4. Infinite positive, infinite negative, that's 5. Infinite negative, infinite positive, that's 6. Infinite negative, that's 7. So we're up to 7. You would have, then you get down to this one, right? And let's see, 7. Infinite negative finite, that's 8. Infinite positive finite, that's 9. So if you're into memorizing, then go ahead and memorize 9. But the best students don't. The best students just get to know the structure of the epsilon-delta proof and understand that it's always kind of the same idea. You have a constraint on y. So if somebody comes in and gives you some constraint, you have an epsilon neighborhood or a very large value that you have to get above or below. And then you have a constraint on x. So a delta neighborhood, or again, a very large value of x that you have to get above or below. And then you make your statements. Well, if x is above that value, or if it's within a delta neighborhood of this value, then the y values, your function's within an epsilon neighborhood of L, or your function's greater than something or less than something. It sounds confusing, but when you start doing it, you really do start seeing all the patterns. Okay, that's just a quick summary. I hope that's helpful. If it's not, well, then sorry. Okay, have a good day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry. Don't